This section we're going to talk about symmetry, and we want to talk about piecewise defined functions. There are, I suppose, just to get going with the idea of symmetry, we've been talking about reflections. If you take a graph and reflect it about the y-axis and consider the original graph together with the reflection, the union of the two graphs are going to be symmetric with respect to the y-axis. Basically, the y-axis kind of runs down the middle. There are points on opposite sides of the y-axis that are equidistant away from it. Let me speak about symmetry in a little bit more generality than that. Basically, when we talk about symmetry, I want to start off by talking about two kinds of symmetry. Line symmetry, or symmetry with respect to a line, and point symmetry. And just see how we would go about constructing this type of symmetry if we're given a partial graph. So let's go with the line. Now, the two key lines we're going to be interested in are the x-axis and the y-axis. For the purpose of this example, I'm just going to draw kind of an arbitrary line that appears to be slanted. So let's go something like that. So there's our line. And let's pick some key points. Suppose we begin with something like this, like there's a point, and there's a point, and there's a point, and there's a point. And I'm going to connect the dots like this, and this, and this. Okay, so some somewhat randomly selected points. Maybe there was some purpose to the way I placed them. But as the graph stands now, it doesn't have symmetry with respect to this line. Okay, it's just kind of there, and there's the line. What I want to do is basically sketch the other half of the graph. Add to this diagram so the resulting picture will be symmetric with respect to the green line. So I'm going to add some points. I'm going to add the images of these four key points with respect to this line. So to construct or to find and then plot the image, you start at a point and then march directly toward the line. Basically choose the shortest path to the line, and then keep on going out the other side the same distance that it took to get you there, and then plot a point. It should be after plotting that point that the line segment connecting the point you started with this new point called the image has the point where it intersects the green line as its midpoint. Okay? And it should also be perpendicular to the green line. So I don't know how good a job I've done with perpendicular there. I'll try to do better with the next one. But that's the idea. So this red point is the image of that point. Do the same thing with the others. March directly toward the line, out the other side, same distance, and then plot that point. Start with this point and march directly toward the line, out the other side the same distance, plot the image, and then finally with the last one. March toward the line, out the other side, plot the image, and there we go. Now, to reflect the line segments about the line, we just connect the dots in the same order that we had them before, and it'll have the effect of reflecting those line segments. So we get this, and we get, now notice the point here that's actually on the line is its own image. So the graph should go through that point like that. And this point is also its own image with respect to the line. And we connect that dot, and then the resulting graph, after we've connected the dots, the union of the light blue graph and the red graph should be symmetric with respect to that green line. It has the green line symmetry there. Okay, so we basically plot the images of all the points on the original graph that we have and take the original graph together with the new one, and that line, that graph is symmetric with respect to the line. Now for point symmetry, it's a little different. So what I want to do is attempt, I probably should have copied and pasted the thing before I included all the other points. So let me do this. And this, I'm going to try to reconstruct that I have. Hopefully I'll get close to it, something like that. And then back up there. Instead of having a straight line through this, what I want is a point Maybe a purple point somewhere in here. Not there. Whoa, wow. What do I want? Control Y. No. All right, let me put the blue point back. Trying to find a good place to put the purple point so it's not in the middle of things. Maybe right there. Okay. So what we want is a graph that is symmetric with respect to that point as it stands right now. And I'm going to include line segments in this. So a line segment there, and a line segment there, and a line segment there. So that's the original graph. As it stands, that's just half of what we need. What we need is another half of that to graph so that the entire graph will appear to be balanced with that purple point right in the middle. So to find the images of these 4 points, we start with each point and we march directly toward the purple point and then out the other side. And then we plot a point, which we call the image of the blue point with respect to the purple point. Do the same thing with the other points. Take that blue point and march directly toward the purple point. Out the other side, the same distance, same direction. And plot a point. To take this blue point, march directly toward the purple point, out the other side. Plot the point, and finally, if there's enough room, and I think there just barely is, march toward the purple point, out the other side, same distance, it's about right there I would guess. And then connect the points in the same order that the blue points were connected in. So the first image I had was this one, so connect to this, and then finally to this one. Does the graph appear to be centered at the purple point? Would you say that's in the middle? The idea with point symmetry is if we pick any point on the original graph, it doesn't have to be one of the 4 key points. It could be maybe this point right here, for example. We have to be able to march directly toward the purple point, through the purple point, out the other side, and when we do that, the image of that point has to be on the graph, and it is. If we pick any point on the red portion of the graph, say pick this point right here, it has to be that if we march directly toward the purple point and out the other side the same distance, its image is also on the graph. So it's points that are basically equidistant from the purple point. Each one has to have its own image. So 2 kinds of symmetry, line symmetry and point symmetry. Now from those 2 kinds of symmetry, if there are 2 particular lines that we're interested in, the x-axis and the y-axis, and 1 particular point that we're interested in, the origin, we get more examples of symmetry. So let's see. X-axis symmetry. Y-axis symmetry, and ultimately origin symmetry. So I believe that's the order in which we're taking these. Small print there, as large as possible. A graph is symmetric with respect to the x-axis if for every point, let's just pick a point right here, convenient point there, xy on the graph, its image, what would be the coordinates of its image? One of the 2 is negative, looks like the same x-coordinate, straight up and down. Both have the same x-coordinate, same distance from the y-axis, same direction from the y-axis, but the y-coordinate's also the same distance from the x-axis, but opposite sides. So if xy is on there, x negative y is going to be on there. So if we've got an equation, here's where this is going to work for us. If we have an equation with x's and y's in it, and we're wondering, what if the graph of that is going to be symmetric with respect to the x-axis? What we'll do is we'll substitute negative y for y. And if when we do that, we can obtain, and we simplify a little bit through some algebraically legal means, if we can get the original equation back, then that will show that the graph of that equation is symmetric with respect to the x-axis, and we'll know that going in before we ever plot any points. Can save time in curve sketching if we have that information in advance. So the graph is symmetric. I think the points I actually plotted were 5, 10, and 5, negative 10 there. Same x-coordinate, opposite y coordinates for x-axis symmetry. So there's the x-axis, let's see, also the y-axis, so y-axis symmetry. What would an example of a graph with y-axis symmetry look like? Maybe this. Graph is symmetric with respect to the y-axis. If for every point x, y on the graph, its image, same y coordinates, because we just go horizontally to the other side of the y-axis, so same y coordinate, but the opposite x coordinate. Whenever xy is on the graph, negative xy is also on the graph. So there's a test for y-axis symmetry that we'll use on some equations in a little bit. We substitute negative x for x wherever we see an x. Simplify. If we can make that equation equivalent or identical to the original equation, then we've shown that the graph of that equation has y-axis symmetry. If not, then it doesn't have y-axis symmetry. And then the third type, origin symmetry. I'll just go ahead and paste what I have there without cluttering the top of the screen with my scribble. A graph is symmetric with respect to the origin. Now the first two were line symmetry. This one is point symmetry. So the point in the middle, now the origin doesn't have to be a point on the graph, but the origin itself does have to be right in the middle of the graph. Whenever the point xy is on the graph, its image just march directly toward the origin. That's not all that direct. Try again. Directly toward the origin and out the other side, the same distance. The point negative x, negative y must also be on the graph. Wherever you start, the point with the opposite x coordinate and opposite y coordinate must also be on the graph in order for the graph to have origin symmetry. So there is a test for origin symmetry. Basically, we take an equation. If xy satisfies that equation, negative x, negative y must also satisfy the equation if it's going to have origin symmetry. So we simultaneously substitute negative x for x and negative y for y, simplify. If we can make it equivalent or identical, if possible, to the original equation, we will have shown that the graph of the equation has origin symmetry. Now, as we do this, to save ourselves as much time as possible, let me postpone the completion of that sentence just for a little bit. To save ourselves as much time as possible, there's one additional observation that we need to make, but I'll make that in a moment. Example 1, for each graph below, determine visually if the graph is symmetric with respect to the x-axis, y-axis, or origin. So, kind, gentle, maybe even fun exercise here. Can we recognize a particular type of symmetry when we bump into it? So this one that looks like a translation of the absolute value function, maybe 3 units downward. What type of symmetry, if any, does this first graph have? Maybe I should have gone ahead and made my observation, because there are actually 5 different possibilities. Maybe I should have mentioned the 5 possibilities. It makes for a great multiple choice question, by the way. 5 I don't want to say 5 types of symmetry. What I said, there are 2 types of symmetry. I said, wait, no, there are 3 types of symmetry. Now we're going with 5 possible scenarios. So let me just say 5 possibilities. A, it may be that a graph has x-axis symmetry only. That is, it has x-axis symmetry, but it does not have y-axis symmetry, and it does not have origin symmetry. Is there a graph like that on this page? Yes, there is. This one right here is symmetric with respect to the x-axis. You take it, you got points up top here. For example, the point 4, 2 is on there, and its image 4, -2 is also on there. If you fold the graph about the x-axis, then the top half, the bottom half will coincide to each other. So that is x-axis symmetry only. It doesn't have y-axis symmetry. It doesn't have origin symmetry. It does have x-axis symmetry. That's one possibility. Another possibility, a graph may have y-axis symmetry only. Is there a graph like that on this page? The first one, this one right here. You take the point 4, 1, and notice that its image, -4, 1, on the other side of the y-axis is also on the graph. So there's that. That graph is not symmetric with respect to the x-axis. Points down below the x-axis. You look up above, and they don't have their images up there. Also not symmetric with respect to the origin. And then there's origin symmetry only. Careful with this one. Is there an example of origin symmetry only on this page? The tone of my voice, the inflection of my voice is expecting a no answer here. I'm trying to telegraph that. Not on this page. There was, I think, on the previous page. This particular graph is an example of origin symmetry only. Right there. That graph is symmetric with respect to the origin, but is not symmetric with respect to the x-axis. You pick xy up there, you look down there for x -y, not going to find it. You see xy right there, you look over for -xy, not going to find it. So it doesn't have x-axis symmetry. It doesn't have origin symmetry. It has, doesn't have x-axis, doesn't have y-axis. It does have origin symmetry, but only origin symmetry. 2 more possibilities. What's the next one? Well, that would make sense, right? That the next one, we've got, you can have exactly 1 of each, or maybe exactly 2 of each. That would be the next logical thing to think. That's what I would think if I had not thought about this before. I would think x and y, x in origin, y in origin. It turns out that those 3 possibilities are actually not possibilities. It turns out that way. The next possibility is all of the above. Suppose we begin with the graph that looks like this. Only consider what's going on in the first quadrant. Suppose we start with that much. So if we just look at what's outlined in red, no symmetry at all. No x-axis, no y-axis, no origin, no nothing. Suppose we want to complete the graph by giving it which type of symmetry? Which type of symmetry would you like to give it? Pick one, x, y, or origin? X. So we want to complete the graph by giving it x-axis symmetry. That means we have to reflect it about the x-axis. So points up top, we have to plot their images down below there. So there's a point, maybe that one, plot its image down there. That's the one on the x-axis is its own image. What we would have to do is that. Okay, so after doing that, all of a sudden, well, not all of a sudden, we just kind of did it there, x-axis symmetry is what this graph has. Does it have y-axis symmetry? Just the red part? No. The red part doesn't have y-axis symmetry. Does the red part have origin symmetry? Nope. Okay, points up here do not have their images down there, not in red anyway. Now, so we've got a graph with x-axis symmetry. Let's add one more type of symmetry to it. Should we add y-axis symmetry or origin symmetry? Which one do you want to add? Y. Let's add y-axis symmetry to this. Now, we're going to take everything in red. We're going to add y-axis symmetry to it. And we'd like to do so in such a way that we preserve the x-axis symmetry, but I don't think there's going to be any fear about losing the x-axis symmetry. So we want to take this point and take it over there, other side of the y-axis. Take this point, take it over there, other side of the y-axis. This point, take it over there, other side of the y-axis. And basically fill in everything we need so that the resulting graph is going to be symmetric with respect to the y-axis. Take it and just flip it over the y-axis, keep what we had, and add the new stuff. So what we have after doing that is the entire ellipse. So we started with nothing, then we had x-axis symmetry, then we added y-axis symmetry, but as soon as we added the y-axis symmetry, what did we get in addition to that? We got origin symmetry. Turns out we can't have exactly two of these three types of symmetry. If we have a graph that has exactly two of these three types of symmetry, it automatically has the third one for free. We can't have two without the other. So all of the above is another possibility. And the fifth and final possibility, and I guess I should have the arrow pointing right there. There's all of the above. Fifth and final possibility is none of the above, yes. None of the above. It's pretty easy to sketch the graph with either no symmetry at all, or at least none of these three specific types of symmetry, just some random scribbles, and chances are it's not going to have x-axis symmetry, y-axis symmetry, or origin symmetry. So I want to keep these in mind. Evidently there's maybe a picture or two on the next page, just the one. And this must be an example of, I'm thinking E, none of the above. Does it have x-axis symmetry? You got a point here. It does not have its image down there, so no x-axis symmetry. Does it have y-axis symmetry? You got a point there. It does not have its image over there. Does it have origin symmetry? Nope. Point there. It's missing its image down there. So it does not have any of these three types of symmetry. Now, does that mean it has absolutely no kind of symmetry at all? Now, it does have some symmetry. We'll talk more about this type of symmetry in section 3.1 when we talk about graphs of quadratic functions. It is symmetric with respect to the vertical line x equals 5. So that's not one of our three types. X equals 0 is the y-axis. That's one of our three types. X equals 5 is not one of our three types that we're particularly interested in this section. So I just want to say, that's not to say this has no type of symmetry at all. I can say none of the above, but that's not the same thing as saying no symmetry, because it is symmetric with respect to that vertical line. It sure looks like this parabola is. See, let's apply these tests for symmetry. Paste those up in the corner, and then apply this to example 2a. So someone hands us the equation 4x squared plus 2y equals 9. Perhaps we have a pretty good idea what the graph looks like. Perhaps we have no idea whatsoever what the graph looks like. What we want to do by applying these tests for symmetry, at least to get an idea if it's symmetric with respect to the x-axis, y-axis, or origin, or if it has none of those three types of symmetry at all. That's basically what the tests of symmetry tell us. Then if we plot a point, what we get is the image of that point for free. When we plot another point, if it has a type of symmetry, we get the image of that point for free. So we can sketch the graph maybe twice as fast as we otherwise would have done so. So we begin by testing it for x-axis symmetry. And just a quick recall here. To test for x-axis symmetry, we substitute negative y for y, wherever we see a y in the equation, and we simplify, and then see if it's, well, I'm going to ask two questions. First, is it identical to the original? If the answer to that is yes, we've got it. If the answer is no, we still may have it. We'll say, is it equivalent? Is there an algebraically legal procedure that we could perform on the equation to get back to the original? So first, substitute negative y for y. So we've got 4x squared plus 2 times an empty set of parentheses equals 9. In place of the y, where the empty set of parentheses are, we're going to substitute negative y. Simplify first. 4x squared minus 2y equals 9. Question number 1. Is this equation identical to the original? Same in every way. Well, one key difference I'm seeing is the plus there and the minus there. So I'm thinking not quite identical. Similar, but not exactly the same in every way. So the next question we would ask, follow-up question, is it equivalent to the original? Is there an algebraically legal procedure we could perform on our equation to get back to the original? And the typical algebraically legal procedures that work in cases like this. Multiply both sides by negative 1. See if that helps. And if it involves a fraction, maybe multiply both the numerator and denominator by negative 1. Maybe that'll help. No fraction here. If we multiply both sides by negative 1, what do we get? Did that help? Did that make it a little bit worse? Yeah. No, not identical to the original, not equivalent to the original. This is simply a no. This one does not have x-axis symmetry because we did not get back the original equation. So keep looking. Y-axis symmetry. Maybe it has y-axis symmetry instead of, well, y-axis symmetry, but not x-axis. So we substitute negative x for x. So 4 times an empty set of parentheses, quantity squared, plus 2y equals 9. So in place of the parentheses, or right in the midst of those parentheses, we're going to substitute negative x, and then entertain a critical question. Maybe 50% or better of college algebra classes recently have gotten this question right, but you got to think carefully before answering. I'm just going to throw it out there. Here goes. Ready? What is the square of negative x? Okay, so the success rate just went down a little bit. That's okay. That's okay. Let's work through this. If we have negative x and we square it, certainly the negative sign is going to be dealt with. Make the negative sign go away. It's going to be negative x times negative x, and we know a negative times a negative is a positive, right? But what is x times x? Yes. This is negative 1 times x times negative 1 times x, which is negative 1 times negative 1 times x, which is positive 1 times x squared, which is x squared. X squared. So when we take negative x and square it, we actually get x squared. So 4 times the square of negative x is 4x squared. Is this equation identical to the original? Okay, yes it is. Okay, so it's identical, it's equivalent, it's all that we could possibly want for this. So we conclude, yes, it does in fact have y-axis symmetry. Now, the one type of symmetry we've not tested for, the origin symmetry. Is it possible that it could have x-axis symmetry, that it could have y-axis symmetry, and it could fail to have x-axis symmetry, but still have origin symmetry in addition? No. We concluded that that a graph, or you believed me, you didn't put up much of an argument, and I appreciate that, that a graph cannot have exactly two of these three types of symmetry. So if it has y-axis symmetry but does not have x-axis symmetry, it's not going to have origin symmetry either. So I'm going to go ahead and conclude y-axis symmetry only. Not x-axis, not origin, just y-axis symmetry here. Okay? B part. Is it unsatisfying in the least to walk away from that previous example without actually looking at the graph? Are you a little bit disappointed that I didn't take time to, we should maybe graph that, maybe solve it for y, punch it into the graphing calculator, and see what that would get? Nobody's disappointed that I didn't do that? Okay, we'll move on then. xy over x squared plus 5 equals 2. Test for symmetry. First of all, let's test for x-axis symmetry. X-axis symmetry. We begin by substituting negative y for y. So x times negative y over x squared plus 5 equals 2. Pick up the y, replace it with a negative y. Certainly the parentheses are crucial here, otherwise it looks like x minus y up there. X times negative y, what is x times negative y? Negative xy. So negative xy, you can actually grab that negative sign since it is a factor of the numerator and drag it out in front of the fraction if you wanted to, or just leave it right there. I think it kind of clearly indicates what's going on here. Can't really simplify it a whole lot more. Is this equation identical to the original? Not identical. Got a negative sign here, but we didn't in the original. How about if we multiply both sides by negative 1? Would that make it identical to the original? Nope. How about if we take the fraction and multiply both the numerator and denominator by negative 1? Does that make it identical to the original? No. So there's some algebraically legal procedures that we can try here, but none of them really work. So again, the answer is no. This graph of this equation does not have x-axis symmetry. Let's check for y-axis symmetry. Y-axis symmetry, begin by substituting negative x for x, wherever we see an x. Negative x times y over negative x quantity squared plus 5 equals 2. Numerator, kind of same as what we got before. Negative x times y also equals negative xy. What is the square of negative x? X squared, yes. Okay, so x squared plus 5 there. Now, we could belabor this, or we could just observe that this and this are the same. So if the first one wasn't equivalent to the original, the second one's not going to be either. So just a quick no. This does not have y-axis symmetry. Now, no x-axis symmetry, no y-axis symmetry. Do we need to bother checking for origin symmetry?
Yes.
Maybe it's possible that it could have origin symmetry, but neither of the other two? I think it's possible. So let's go ahead and check origin symmetry. So what we've seen is if we substitute negative y for y and simplify, it's not equivalent to the original. If we substitute negative x for x and simplify, that's not equivalent to the original. But if we substitute negative y for y and negative x for x at the same time, maybe the outcome will be different. Negative x times negative y over negative x quantity squared plus 5 equals 2. Negative x times negative y is xy. Square of negative x, x squared. And there we go. Okay. Multiplying the negatives together gave us a positive in the numerator. This is identical to the original, so it's big yes for origin symmetry. 4 minutes and change. I don't know if we can do 2 more. We can certainly do 1 more, though. We might be able to do 2 more. 3y squared minus x equals 4. Cool graph, by the way, the B part. We're going to take the time to sketch the graph. I think you like it, but let's move on. X-axis symmetry. Substitute negative y for y. 3 times negative y quantity squared minus x equals 4. What is the square of negative y? Y squared. So this is going to be 3y squared minus x equals 4. Is this identical to the original? Yes. It is. So right off the bat, we get a yes for x-axis symmetry. How about y-axis? 3y squared minus negative x equals 4. Simplify just a smidge. 3y squared plus x equals 4. Is this identical to the original? If we multiply both sides by negative 1, will that make it identical to the original? No. So I'm thinking no. What can we say about origin symmetry? We can say no. So x-axis symmetry only. Oh, that barely took a minute. We can go ahead and do the D part. Go ahead and do the D part. 4x squared plus 9y squared equals 36. What's your gut telling you here?
Yes, yes, yes.
I'm thinking yes, yes, yes. X-axis, y-axis, origin. Yeah, substituting negative y for y is going to give us the 9y squared right back. Substituting negative x for x is going to give us the 4x squared right back. And doing both is going to do both. What does the graph of this look like? Anybody know? It's, well, the 4 and the 9, since the 4 and the 9 are different from each other. If they were the same, it'd be a circle. But because they're different, you got a little bit more y squared than x squared. It's actually an ellipse. So the picture, if you think y-intercepts, no, if you think x-intercepts, I think plus or minus 3. Check it, but I think plus or minus 3 on the x-axis, and maybe plus or minus 2 on the y-axis. So it's a circle maybe that somebody sat on. Something like that, I believe is what the graph looks like. And still time to look at what we'll do next time. Whoa, too late to begin that. Even and odd functions next time. Also what? Piecewise defined functions. Functions that are increasing or decreasing on an interval. Wow. Okay, so still a good bit. Oh, and relative extrema. Relative maximum minimum point. So still a good bit in section 2.7. Hopefully finish that next time, and I'll see if I can get 2.8 posted for you. All right. Thank you much. Not every function that we'll run into falls into the category of even function or odd function, but there are quite a lot of common functions, useful functions, that do fall in one of those two categories, and when a function does, when it can be classified as either even or odd, we want to call attention to that and exploit its properties. We get a lot of information for free. We're going to see right away a connection between symmetry and evenness and oddness. The 6 trigonometric functions, sine, cosine, tangent, cotangent, secant, cosecant, all 6 of them fall into one of these 2 categories, even functions or odd functions, and there are others that we'll look at. A lot of polynomials fall into the category of either even or odd. So definitions. Function is even if f of negative x equals f of x for all x in the domain of f. Now for this to be true, the domain has to be symmetric with respect to 0. Basically, if 19 is in the domain, that means negative 19 has to be in the domain. If negative pi over 6 is in the domain, that means that positive pi over 6 has to be in the domain. That's implicit in this definition. Function is odd if f of negative x equals negative f of x for all x in the domain. So let me copy and paste. Actually, I think I've already done that. Copy and paste these definitions. No, I haven't. Let's do it now. And then see what the pictures look like. See what connection it has to the symmetry that we talked about recently, and then look at some examples, see if we can show algebraically whether a function is even, odd, or neither even nor odd, and then show it graphically. So, even function, let's see what it might mean. So, let's see if I can attempt to draw an even function. What it might mean for f of negative x to equal f of x for all x in the domain. So let's pick an x, and let's imagine it's got to be defined to be something. It could be 0, could be positive, could be negative. I'm going to imagine that it might be positive. If f of x is positive, that means there'd be a point up above the x, up above the x-axis. So that's the point. I'm going to call it x f of x. Now, domain is symmetric with respect to 0, so if x is in the domain, that means negative x is also in the domain. So let's go over here, right there, and try to figure out what point I've got to plot with an x-coordinate of negative x. Well, if this is true, if the point, how to say this, somewhere I've got to plot a point, negative x, f of negative x, and according to that, the y-coordinate of that point is exactly the same as the y-coordinate of this other point that I just plotted. So it needs to be directly across the y-axis, so it's got to go right there. The x-coordinates are opposites of each other. The y-coordinates are the same. This statement, this requirement on this function is equivalent to saying the graph of this function is symmetric with respect to the y-axis. We can plot a whole lot of other points, but whenever we plot a point, we look at the point that has an opposite x-coordinate, it's got the same y-coordinate, it's going to be on the other side of the y-axis, the image of that point. That's what's going to happen. So just as an example of what an even function might look like, kind of a simple one, maybe something like this, and something like that. It could keep on going up there, it could keep going up there, but we pick a point, any point, look at its x-coordinate, we know, and look at its y-coordinate. We know there's another point on that graph with the opposite x-coordinate, but exactly the same y-coordinate, the image of that point on the other side of the y-axis. So if a graph is the graph of a function, okay, it's a function, and it has y-axis symmetry, then it's going to be even. And if it's an even function, then its graph will have y-axis symmetry. Now it's possible for a graph to have y-axis symmetry like, what? Whoops. Come on, y-axis symmetry. There we go. It's possible for a graph to have y-axis symmetry, fold that thing on the y-axis, but not be a function. So just because it has y-axis symmetry doesn't mean it's an even function, because it might not be a function. But if it's a function, if we can erase part of it, make it a function, come on. There we go. Oops, put that back. So if we can erase enough of it to make it a function, then it's an even function. That passes the vertical line test, and if that is symmetric with respect to the y-axis, then it is an even function. So even functions can be characterized like this. What about odd functions? Well, what about them? Let's see if we can graph one. What might it look like? Well, let's start with an x. f of x has to be something. If it's in the domain, I'm just going to start with basically the same point there, right there. Suppose that's the point x, f of x. You evaluate it, you get maybe a positive number, and you put it right there. Now, since x is in the domain, negative x is also in the domain. So let's go over here. And we've got to plot a point with an x coordinate of negative x. According to this, the y-coordinate of the point that has an x-coordinate of negative x is exactly the opposite of the y-coordinate of the point with an x-coordinate of x. So, same distance from the x-axis, but other direction. There it is. There's negative x, f of negative x. Notice that if we were to connect those dots with a straight line, that straight line would pass through the origin, I should say line segment. That line segment would pass through the origin, and the origin would be the midpoint of that line segment. And that's equivalent to saying that this graph, no matter what other points we put on it, has to be symmetric with respect to the origin. Okay, so we could connect the dots and do something like, oh, I don't know, maybe something like this. A lot of ways we could connect the dots, but however we connect the dots, wherever we plot a point, its image on the other side of the origin has to be there. So if we're going to call a function odd, its graph is going to have origin symmetry. If we're going to call a function even, its graph is going to have y-axis symmetry. Now, when we start classifying these functions as even, odd, or neither even nor odd, the question might arise because it takes a little bit of work to show that a function is even. If we show that that function is even, we might want to ask ourselves before moving on, is it possible that it could also be odd? I mean, whole number, can't be both even and odd the way they're defined, but functions are different. So if we show that a function is even, is it going to be possible that that function is also odd? What are the implications there? If it's even, its graph's going to have y-axis symmetry. If it's odd, its graph is going to have origin symmetry. So, if it's both even and odd, its graph has to have both kinds of symmetry. See where I'm going with this? And if its graph has both kinds of symmetry, then what else? What other kind of symmetry does it have to have if it has y-axis symmetry and origin symmetry? It's got to have x-axis symmetry. And that's difficult for the graph of a function. It's possible, I mean, you have to use your imagination to imagine a graph that passes the vertical line test and is symmetric with respect to the x-axis. If I just said, okay, everybody take out a sheet of paper and draw a graph, just use your imagination, try not to be, obscene or anything like that, but just use your imagination and draw a graph that's symmetric with respect to the x-axis, probably it's going to fail the vertical line test. Right? If I just did that, I would think, oh, okay, what? One of those sideways parabolas, something like that. Close to x-axis symmetry, but it fails the vertical line test. In fact, as soon as I plot a point that's not on the x-axis, and I say, okay, this is half of the graph. I want to make sure that if I plot the next point, it's going to be symmetric with respect to the x-axis. Where does the next point have to go? Right there. And just like that, plot 2 points, it fails the vertical line test. So is it possible for the graph of a function to have x-axis symmetry? Well, yeah, only if its only points are on the x-axis. And that's not really exciting, right? That's basically, let the domain be whatever you want it to be, but that's the only function that can have x-axis symmetry. It's also the only function that can be both even and odd. Let the domain be the set of all real numbers. Its graph is the x-axis. There it is. That's the only function that's both even and odd. So at some point in the next few minutes, we'll show algebraically that a given function is even. And then I'll ask, well, is it possible that this function could also be odd? And then we'll say, well, is it this function? Because that's the only one that can be both even and odd. And if the answer is no, it's way more exciting than the 0 function, we'll say, nope, okay, it's even. It's not possible for it also to be odd. So we'll move on to the next example. So here goes. Let's see if we can do this. Problem says find f of x and classify each function as even, odd, or neither even nor odd. So we'll begin by checking to see if it's even. That's usually the easier thing to do. If it's even and it's not the 0 function, we'll just stop and move on to the next problem. If it's not even, we'll take another couple steps and check and see if it's odd. And then if it's not odd either, then it's neither even nor odd. So in each case, we find f of negative x. In the definition, for evenness, we're looking for f of negative x to equal f of x. And for oddness, we're looking for f of negative x to equal the opposite of f of x. I'm going to show one of those two things, otherwise it's neither even nor odd. So substitute negative x for x wherever we see an x, just the one spot where we see the x. And let's see if we remember how we did this last time. Here we go. What is the square of negative x? Yes. So 2x squared minus 5. So we substitute negative x for x, and this should sort of feel like what we did to check for y-axis symmetry. Remember that? We're checking for y-axis symmetry. We substitute negative x for x, simplified, and then ask ourselves if it was equivalent to the original. Where here we substitute negative x for x, simplify, and ask ourselves, is this expression identical to that one? It is. So right off the bat, what we found is that f of negative x equals f of x. So this function is even. This function is an even function. And so I guess one other question, is it possible that this function could also be odd? No, because the only function that's both even and odd is the 0 function, and this is not the 0 function. So it's even, it's not odd. Next, f of x equals this rational function here. F of negative x equals 4 times negative x over 3 minus the square of negative x. F of negative x equals negative 4x over 3 minus, I think we're all good with the fact now that the square of negative x is x squared. So let's put an x squared there. So first question, is this expression identical to that one? No. I guess another question might be, is there an algebraically legal procedure that we could perform on this to make it identical to the original? Now, when we were testing for symmetry, we had an equation, so we had the luxury of multiplying both sides by -1. We no longer have that luxury, but we still have the luxury of multiplying both the numerator and denominator by -1. If we did that, we can make that 4x in the numerator, but the denominator would become -3 plus x squared. And I don't think we want that in the denominator. It wouldn't hurt, it just wouldn't be identical to the original. So this is, make some notes here, not f of x. So the function is not an even function. But it still could be odd. So what we do, if we're thinking maybe it's odd, we could look at it and ask ourselves, does this expression equal -1 times the original expression? You think? I'm thinking the negative sign kind of conspicuously shouts that out. It does look like it's -1 times the original. So if we grab that negative sign, since it's a factor of the numerator, grab that negative sign, bring it out in front of the fraction. That's an algebraically legal thing to do. Makes an equivalent expression. Negative of 4x over 3 minus x squared. And then cover up the negative sign. Where is it? Can I reach that high? Cover up the negative sign and ask ourselves, is that expression identical to the original?
Yes.
And it is. So f of negative x equals the opposite of f of x. And that shows that the function's odd. So it's odd. And if we were to sketch the graph of this first one, y equals 2x squared minus 5, would be symmetric with respect to the y-axis. The graph of the other one, we'll trick your graph in that. We'll graph expressions like this, functions like this. In section 3.5, when we talk, or is it 3.6? I can't remember. When we look at rational functions, but you want to enclose the 3 minus x squared in parentheses, 4x divided by the quantity 3 minus x squared. Look at that picture, and it is symmetric with respect to the origin. Origin symmetry it has. Two more to check. F of negative x equals 3 times negative x to the 5th plus 2 times negative x to the 3rd minus 4 times negative x. When we simplify this, keep in mind negative x to the 5th has 5 negatives all multiplied together. Negative x times negative x times negative x times negative x times negative x. If you multiply 5 negatives together, 4 out of 5 multiply together to equal a positive. An even number. A couple negatives make a positive, a couple more negatives make a positive, and we're left with one negative. We can write that as negative x to the 5th. Grabbing that 5, bring it on the inside of the parentheses, transforms that from being 5 negatives all multiplied together just to being 1. So plus 2 times negative x to the 3rd. That goes from 3 negative x's multiplied together just to negative 1 times x to the 3rd power. And then plus 4x, I think we can get by with saying subtracting negative 4x is equivalent to adding positive 4x. So f of negative x equals negative 3x to the 5th minus 2x cubed plus 4x. Once it's completely simplified, we look at it, we ask ourselves, is this identical to the original? Same in every way. Is it? Some conspicuous differences here. Where there's a positive 3, there's a negative 3. Where there's a positive 2, there's a negative 2. Where there's a negative 4, there's a positive 4. So not exactly the same, is it? So not f of x, so it's not even. Is it exactly the opposite of the original? Is it negative 1 times the original? I'm thinking maybe so. We can see that clearly if we factor out a negative sign and write this as the negative of 3x to the 5th plus 2x cubed minus 4x. Factor out a negative 1 or a negative sign. And then look on the inside of the parentheses. Look on the inside of the parentheses, cover up the minus. There we go. I hope I don't break it. There we go, cover up the minus. And what's inside the parentheses, if that's identical to the original, then we're looking at an odd function here. F of negative x equals the opposite of f of x. Therefore, f is odd. And if we were to graph this, we'll look at some graphs of even functions and odd functions in a little bit, we would see that its graph is symmetric with respect to the origin. Symmetric with respect to the origin. Now, what would a function that's neither even nor odd look like? We've got so far an even one, a couple odd ones. We'll notice in a GeoGebra worksheet that I'm going to take time to show you in just a little bit, is if all the exponents, if it's a polynomial function, you have to be careful. This applies to the A part, the B part, and the D part. The B part is a different animal. That's not a polynomial, that's a rational function. It's a ratio of 2 polynomial functions. But if it's a polynomial function and has nothing but even exponents, there's a 2 and there's an invisible one, which is 0, 10.
Won't it always be odd?
What's that?
Can't it always be odd?
Can't it always be odd?
Why won't it always be odd? Because all you're doing is taking the original and just putting the negative outside.
Well, we're taking the original and we're substituting negative x for x. I mean, this one, because we're squaring the negative sign vanishes. And so that, you kind of, when you substitute negative x for x like that, the negative goes away. So after doing that, you no longer have the negative, and so it wouldn't be the opposite of the original. You just get back the original. So we substitute negative x for x, the negative sign vanishes, and we get back what we started with, so that makes it even. If the exponents are odd, like in the C part, you substitute the negative in there, and you still have negatives. And so that's going to be an odd function. If it's nothing but odd exponents on your polynomial function, it'll be odd. If it's a mixture of even and odd exponents, it's going to turn out to be neither. It's not going to be an even function or an odd function. I don't know how that worked with your question, but that's the even exponents tend to eliminate the negatives. The odd exponents, they linger, and so you end up with odd functions if it's nothing but odd exponents on the polynomial. Anthony?
So you're always substituting negative x for f of x.
For every x, yes.
But, well, I mean, I know,
Yes.
according to if it's f of x.
Sure, yeah.
But if it's f of negative x, you'd substitute x.
Whoa.
Is that or is it always going to be f of x equals
So we start with the function f of x.
Right.
Okay. I'm worried that you're thinking we're starting with f of negative x, and that's.
Well, I'm just saying.
So we start with f of x. F of x equals blah.
Yeah.
To answer the question, is it even or odd? Calculate f of negative x.
Right. The opposite.
Yeah. So you substitute. Well, I don't want to call it the opposite. Substitute negative x for x.
Right.
And if it gives you back exactly what you started with, you're dealing with an even function. If it gives you back the opposite of what you started with, then you're dealing with an odd function.
Right. So you're never going to have a problem that asks for f of negative x equals, and then you substitute. You see what I'm saying? Like if you had a d was f of negative x equals 2x to the fourth plus 5.
Right.
And so on.
Yeah, that almost sounds like, and I don't know why I have an extra f of x here.
I guess my point is,
Yeah.
if you run into that situation, you're always thinking about substituting the x value the opposite of what it's asking you. Is that right? Do you understand what I mean?
I think so. I just think it's maybe just worrying too much to think that you're going to be handed something that says f of negative x.
Right.
At some point, you got to get back to what's f of x?
Right.
What's f of x? There might be some work to figure out what f of x actually is.
Oh, so you're always going to start.
But you got to start with f of
f
x.
of x.
And then once you start with f of x and it's clear in everybody's mind what f of x is, then you can substitute negative x and then try to answer the question, was f of x even or was it odd?
Okay.
Yeah.
And you're always going to jump from the platform of f of negative x and substitute negative x into the value
Right.
of x. Okay.
So watch what happens here. You substitute negative x for x wherever there's an x. The terms that have the even exponents cause the negatives to disappear. Right, negative x times negative x times negative x times negative x. There are 4 negatives, which multiply to equal a positive. There are 4 x's that multiply to equal x to the 4th. And so you have just 2x to the 4th. On the other hand, the negative x quantity to the 3rd power ends up being negative x cubed. And so the negative sign lingers. But the negative sign vanishes on the even exponent. So we look at this expression and we ask ourselves, is it the same as the original? And the answer would be no. The one that had the odd exponent changed its sign. So it's not the same as the original. If we factor out negative 1, so not f of x, so it's not even. But if we factor out a negative 1, change all the signs and put a negative sign in front.
Yeah, right there. Where did you get the -2 and then the +8?
Well, I'm just trying to answer the question, is this expression the opposite of the original? So if I'll factor out a -1 and then look inside the parentheses, if what's inside the parentheses is identical to the original, then the expression I'm dealing with is the opposite of the original. But if after factoring out a negative sign, what I have is not identical to the original, then it's not equal to the opposite of f of x either. So it's neither even nor odd. I mean, I don't technically have to factor out that negative sign. I suppose that could seem a little strange to have to do that. Let's just scoot it down here and kind of ignore it for the moment. So suppose we don't do that. Just look at this expression Can we answer the question? Well, I know we can answer the question, is this identical to the original? No, because you got a plus 5x cubed, you got a minus 5x cubed. It's not the same. Well, is it exactly the opposite of the original? Well, no. I mean, the minus 5x cubed is the opposite of 5x cubed, sure, but the 2x to the fourth are the same. And the negative 8x squareds are the same. So it's not exactly the opposite of the original. So for that reason, f of negative x is not equal to negative f of x. That arrow is kind of in the way there now. So for that reason, it's not odd either. It's not the same as the original, not the opposite of the original, so neither even nor odd. Now, what do even functions look like? What I've done here is, this is the graph of the function f. The graph of the function f, and this is what the function f looks like. It's nothing but even exponents, and its graph has y-axis symmetry. If we change the coefficients, I'm just going to mess with the coefficients here. Like, we'll change the coefficient of a to it. Well, okay, that changed it a little bit. Changed the coefficient of the x to the fourth term. I wish we didn't see that g of x there. That's bothering me. Let me see, what is this? That's h. So go away, g of x. I only want to see you if I check the odd function box. Okay. Now, so we're looking at this, and you've got nothing but even exponents on that polynomial. We can mess with the coefficients, but no matter how we mess with the coefficients, notice the new graph is still insisting on having y-axis symmetry. So if you've got a polynomial function with nothing but even exponents, and the 15 there on the end, that's 15x to the 0 power. X to the 0 power is 1, so we don't have to write the x. That counts as an even exponent. So whatever we do, the graph is going to be symmetric with respect to the y-axis. On the other hand, let's check the odd box. There's the odd box, and now I want that function f to go away. What was even was that? That was e, so let's go away. Put an e there, and then it'll go away. So we've got nothing but odd exponents here. Nothing but odd exponents, 7, 5, 3, and 1. We don't want a constant term because, again, that counts as x to the 0 power, even exponent. Notice the graph, if we alter the exponents, not the exponents, alter the coefficients, change the coefficients somehow, some way, the graph looks different, but every single modification we do to the graph, it continues to have origin symmetry. Every single one of these graphs is symmetric with respect to the origin. Let's go with a positive coefficient, leading coefficient there, and maybe change that up. Whoa, there we go. There's some crazy behavior some of these polynomials have, but they all these, if nothing but odd exponents, it has origin symmetry, symmetric with respect to the origin.